Alright, so today we're covering more specific properties of this system we started with our last video. And we're going to starting out with orthogonality properties. And so we're going to be looking at the root space decomposition for, we're going to use the killing form. And just recall that we already have some basic insight into how this is going to go. Got the killing form of the eigenspace of a root alpha and a root beta is 0. If alpha and beta are in H star and their sum is non-zero. And we saw in particular that the killing form of our Toral subalgebra with L alpha is 0 for all alpha in phi, so that the restriction of the killing form to our Toral subalgebra is non-degenerate. That was what we basically went through last time. And we're going to start out with a proposition with no preamble, just parts. First off, we have that our Toral subalgebra spans the dual space of the set of roots spans the dual space of our Toral subalgebra. We have that if alpha is a root, then so is its negative. Now we have if alpha is a root with an eigenvector L alpha and an eigenvector of its negative, so of x and y respectively, then the bracket of x and y is equal to the killing form of x and y multiplied by the equivalent of the root alpha in our space. Remember last time we saw that we can identify H star with H, and there's a canonical corresponding element of our Toral subalgebra for every root. That's what that element is. Continuing on for D, for all alpha, if alpha is a root, then the bracket of L alpha and L negative alpha is one-dimensional with a basis is going to be a single element, of course, and that is going to be our T alpha. E is going to give that applying a root to its own element is equal to the killing form of that element with itself, and is also going to be non-zero for all alpha in our root space. F is that if alpha is a root and we have with an eigenvector x alpha being non-zero, there exists a y alpha in the L negative alpha such that X alpha, Y alpha, and a new element we're going to call H alpha, which is defined to be the bracket of these two. You can probably see where this is going. Span a three-dimensional simple subalgebra of L isomorphic to SL2. Hopefully you should start to see why our study of that was important from our past couple of videos. Isomorphic to SL2F with each element being sent to the element you would expect. X is the upper triangular, Y alpha is the lower triangular, and H is the reflection. And G states that in this case, our H alpha is equal to 2 times our T alpha over the killing form of T alpha with itself, which as we saw above is non-zero once we get around to proving that H alpha is the opposite of its opposite. You see what I mean. Now, a lot of different things to prove here. Let's go over them one by one. A is just that our root space, our set of roots spans the dual space. So A. If V does not span H, then we can let H be in H non-zero such that alpha H is equal to 0 for all alpha in our root space. Thus, the bracket of it with each of our alphas is 0 for all alpha in the root space, for every root alpha. Now, since the bracket of H with its total subalgebra has to be 0, then the bracket of H with all of L must be 0, so H is a member of the center of L, which is 0. Alright. B states that every root has a negative, so we're going to let our alpha be a root. If negative alpha is not a root, so that our L negative alpha is trivial, then we have that the killing form of L alpha and L beta is 0 for all beta in H star. So the killing form of L alpha with all of L is 0, and K is, our killing form is degenerate, which is another contradiction. C was that if you have x in L alpha and y in L negative alpha, then the bracket of x and y is the killing form of x and y times t of alpha. So we're going to pick a root, x in L alpha, and y in L negative alpha. So we want the bracket of these two is the killing form times that version of alpha. So we're going to let h be some element of h. Then we have, once again, want to stall for some room, the killing form of h with the bracket of x and y, which we're trying to determine, is equal to the killing form of the bracket of h and x with our y, which is equal to alpha of h times the killing form of x and y, which is equal to the killing form of t alpha and h for our times the killing form of x and y, which is the killing form of x and y times t alpha with h, which is equal to the killing form of h with the killing form of x and y times t alpha. So if you look at this, the start and where we ended up, we see that our h is orthogonal to, at the start, we have the killing form of h with x bracket y, and at the end we have it of the killing form of x and y t alpha. So this component on the right, so this whole thing must be 0, so the bracket of x and y must be the killing form of x and y times t alpha, which is just what we wanted to show. Now D states that the bracket of the space of a root with its negative is one-dimensional, with the basis being this t alpha. So D. From the previous part, we have that T alpha spans, see from above that T alpha spans L alpha bracket L negative alpha when it is non-zero. Let x in L alpha be non-zero. Then if the killing form of x from L alpha and L negative alpha is 0, then the killing form of x and L is 0 as by means of B. But this is a contradiction. Thus, we have a non-zero y in L minus alpha for which I will write as with k of x and y being non-zero. From C, this gives that the bracket of x and y is non-zero. Part E, which states that the root on its own T alpha, root alpha of its own T alpha is equal to the killing form of T alpha with itself, which is non-zero. Suppose that alpha of T alpha is 0, so that the bracket of T alpha and x is E0, which is going to be T alpha of y for all x in L alpha and y in L negative alpha. As in D, we have x and y such that the killing form of x and y is non-zero. And by scaling, we can just let the killing form be 1 to keep things simple. Then the bracket of x and y is T alpha by C. And is E the, yeah. Sorry, I had to double check something. Thus, the subspace S in L spanned by x, y, and our T alpha is a three-dimensional solvable algebra. With S isomorphic to its adjoint in L inside of the general linear Lie group, Lie algebra of L. With the L adjoint of S nilpotent for all S in the derived algebra of this subspace. So the adjoint L of T alpha is both semi-simple and nilpotent. So the L adjoint of T alpha is 0. Thus T alpha is in Z of L is 0, which is a contradiction. Therefore alpha of T alpha is non-zero. F, which states that we can reconstruct SL2 let X alpha and L alpha be non-zero. And pick Y alpha in L negative alpha such that the killing form of X alpha and Y alpha is equal to 2 over the killing form of T alpha with itself. This comes from E and from the killing form of X alpha with L negative alpha is going to be non-zero. Set H alpha to be equal to 2 T alpha over the killing form of T alpha with itself. Then we have that the bracket of X alpha and Y alpha is H alpha by C. And that the bracket of H alpha and X alpha is 2 over alpha of T alpha times bracket of T alpha and X alpha, which is going to be 2 of alpha T alpha times X alpha over alpha of T alpha, which is just going to be 2X alpha. And similarly, the bracket of H alpha and Y alpha is negative 2Y alpha. So the multiplication table is going to be the same and everything follows from that. Finally, we have part G, which states that as G was that H alpha is 2T alpha over the killing form of T alpha with itself. T alpha is defined by K of T alpha and H being equal to alpha of H, all H in H. We have that T alpha is equal to negative T of negative alpha and the rest is computation. And that's the end of both this or set a proposition. And that's actually going to be this whole chapter, just kind of working through these properties. And now we're going to be working through more properties, kind of in a different context. These are going to be integrality properties. I'll start with the preamble for each pair alpha and negative alpha. These are roots, of course. We're going to let S alpha be the copy of SL2F in L as constructed above. By Weil's theorem and previous results, we have a description of all finite dimensional S alpha modules and can describe the L adjoint of S alpha. Is this all just, it's not all discussion, but it's mostly discussion. Sorry. So we're going to fix a root alpha in the set of roots. Let M be the subspace of L spanned by H and root spaces, all root spaces of the form L of C alpha for C in the dual space of our F, our field. This is an S alpha submodule of L. And the weights of H alpha on M are integers 0 and 2c equals c. Alpha of H alpha from above so all C must be half integers, which is just half an integer. You know, S alpha acts trivially on its kernel, obviously, the kernel of alpha. Which is a subspace of codimension 1 in H, complementary to F times H alpha. While S alpha itself is an irreducible S alpha submodule of M. Thus, kernel of alpha and S alpha, exhaust the occurrences of weight 0 for H alpha. So the only even weights occurring in M are 0 and plus or minus 2. Thus, double root is never a root. And so logically, when half a root cannot be either. So 1 cannot be a weight of H alpha in M. From what we've seen from previous results, we have that M is equal to H plus our S of alpha with the dimension of L alpha being 1, making S alpha uniquely determined as the subalgebra of L generated by the eigenspaces of L alpha and L negative of alpha, and the only multiples of a root are root alpha, which are roots, are our guaranteed positive and negative of alpha. Now, how does our S alpha act on root spaces of L beta where beta is not related to alpha? We're going to set K to be the sum of L of beta plus I alpha for integer I. We have seen each root space is one-dimensional and no beta plus I alpha can be 0. So K is an new page. S alpha submodule of L with one-dimensional weight spaces for distinct integral weights beta of H alpha plus 2I with I being an integer such that beta plus I alpha is in our root space. As we cannot have both a 0 and 1 as weights of this form in this form, K, as we've seen, is going to be irreducible. The highest weight must be beta of H alpha plus 2Q, and lowest being beta of H alpha minus 2R if Q and R are the largest integers such that beta plus Q alpha and beta minus R alpha respectively are roots. Also, the weights on K form an arithmetic progression with a step size of 2. So that the roots of the form beta plus I alpha form a string of beta minus R alpha up through beta up through beta plus Q alpha, which is called the alpha string, through beta, we notice that beta minus RA of HA is negative of beta plus Q alpha. 1 second, I'm going to write this on a new line because this is getting hard to read, even by my standards. So we have that beta minus R alpha of some H alpha is the negative of beta plus Q alpha of H alpha, so that beta of H alpha is just R minus Q. And we notice that if alpha, beta, and their sum are roots, then from previous results we know that the adjoint of L alpha maps L beta onto L alpha plus beta. Once again, we have a summary of all our results here as a proposition. Proposition. Part A is that for all roots alpha, we have that the dimension of their eigenspace is 1. With S alpha being equal to L alpha plus L negative alpha, plus H alpha for H alpha being equal to the bracket of L alpha and L minus alpha. And for a given non-zero X alpha in L alpha, there exists a unique Y alpha in L negative alpha, such that the bracket of X alpha and Y alpha is equal to H alpha. That's part A, 106. My hand is getting tired, so I need to give it just a quick second here. Beta. For all alpha being a root, the only multiples of alpha that are roots are our positive and negative alpha, C. For all alpha and beta being roots, then beta of H alpha is an integer called the Cartan integer. And beta minus beta of H alpha times alpha is also a root. D is if we have roots, two roots with their sum also a root. Then their bracket, we've already seen this, the bracket of their eigenspaces is the eigenspace of their sum. Condition E, let alpha and beta be roots, with beta distinct from alpha. Let R and Q be the largest integers such that beta minus R alpha and beta plus Q alpha are roots. Then beta plus I alpha is a root for negative R less than equal to I less than equal to Q. And we have that beta of H alpha is equal to R minus Q. And finally, L is generated by our root spaces. And yeah, that's the end of this section. We've got, oh man, okay, we've got, did we go for it? We have one more section and then we're done this whole chapter. How long was the first video? I think did we go for it? Or it kind of ties into, you know what? Given how closely the next chapter ties into the next section ties into the next chapter, and given how important that is, I think I will let us split across chapters next time, and we will call it here. And we've just hit our episode length anyways, so wouldn't want to spoil that.